Hello everyone. So let's continue the presentation. The good news is that my stylus is here, so now my handwriting is going to be better. So let me share with you my the PDF that we were talking about. So basically, last time. In last video, we got to two equations. One is this stress sigma 1 and sigma 2 stress, axial stress in tablet 1 and 2, and shear stress in the mortar. We call this equation 6. So equation 6 is our stress values. Now, what we want to calculate is, if you remember from the get-go, when we were looking at the slides, we were interested in energy dissipation. We were interested in toughness, things that strength and toughness. And we were also interested in stiffness. So we have to be able to extract these properties from these calculations. But all of these, when we're talking about the stiffness, it's not just the stress, it's also about the strain. It's the ratio of the two. When we talk about energy, it's the area under the stress-strain curve. So we have to, either way, we have to calculate displacements and strains. When we have stresses, the good news is we have a way to calculate the strains. And keep in mind that so far, we're only focusing on linear response of the material. So now, if you look at, this is tablet 1 and this is tablet 2, if you look at tablet 2, at this far end here, we know that the displacement is 0. So basically, we know U2 of 0 is 0, okay? So, and that's a very good boundary condition. It's the best boundary condition that one can imagine, basically, because it means the constant of the integration is 0. But the differential equation we have to solve is actually this one. Epsilon 2, which is the derivative of U2 with respect to x, we can calculate it based on sigma 2 that we already have, and this is our boundary condition. From equation 6, and this is what we know from equation 6. So if we add that to the to this equation and integrate it, we can get U2. But we are interested to see how far this end moves. And actually, this end moves by U1 of L. So we have to calculate basically U1. We need to see what U1 is. The other good news is that U1 and U2 are related to the shear strain like this. You remember we had, in the past, we derived U1 minus U2 divided by H. This is the same equation. So this is just, so now that I have U2, I can put it in here. And instead of gamma, I can just put tau over G. This is the G of the mortar. And tau is again from equation 6. I have tau again from equation 6. I can put both of them in here, and that allows me to calculate U1. Keep in mind, in principle, I don't have any boundary condition for U1 because both ends of this guy will move. So there's no point that ahead of time I know the value of U1. There's no point, which means I have to do I have to find it starting from this point that I know displacement, walk my way through tablet 2, then, or brick 2, then mortar, then get to tablet 1. So, so basically, this is The result of the calculation is what you see here, equation 7. So U2 was calculated earlier on this page. Gamma was calculated as the ratio of the shear stress to G, shear stress in the mortar to the shear modulus of the mortar, and you get a simple, well, simple or complex. I mean, it doesn't matter at this point. You get the value of U1. So now, now if this is my, I'm interested to calculate the strength of this guy. I'm interested to basically the force it takes or the average stress it takes for this guy to enter plastic limit. So the stress that is applied at this, the force that is applied here is sigma 0 times B times 1. And this is actually, if you look at this building block, this is the area of this guy is this whole thing, which is 2B plus H times 1. 1 is the unit thickness of the whole guy. Therefore, the average stress in this guy is sigma 0B divided by 2B plus H. Okay? In other words, the total force, which is this guy, the numerator, divided by the total area. Okay? And so so sigma 0 is actually the stress that is applied at this far end. And if you know that, if you want to see how shear stress or shear stress in the mortar and the stress, axial stress in each of the bricks, let me just check my time. And the axial stress in the bricks scale with change as a function of x. These are these two plots. So these are both of them. These are the plots of equation 6. Here, this is strictly in the mortar, and this is strictly in the bricks. Okay. And so now and this sigma 0, this is only for this far end. Now, basically, because the whole thing is in equilibrium, it means the average stress at every cross section has to be the same value, has to be this, because the force applied on the far end is this. So now, this allows us, this area that we have here allows us to calculate the average or effective stress in the tablets, which is going to be this much. And we can also calculate strain, effective strain in the tablet. This effective strain is, or average strain, is basically nothing but the ratio of, so this is change in length divided by the initial length. Change in length divided by the initial length. The farthest point of the tablet moves by this amount, and I can calculate that from equation 7. And that allows me to calculate the effective strain in the tablet caused by an effective stress, this. The ratio of these two, this and that, will give me the effective stiffness of this guy, which we can easily calculate, and it's shown in here, in equation 8. So now I can plot this equation 8, and so basically the effective strain, So this is equation 8 that is plotted here, is shown here. Again, we choose basically the x-axis is the product of lambda L, or L overlap length in units of 1 over lambda. Remember, lambda is 1 over length, so 1 over lambda is length. And so, for instance, you can easily look at equation 8, and you can see that it's a function of lambda L, lambda L. And so when you plot that, you see that, for instance, when lambda is equal to 5L, we are, or L is equal to 5 over lambda, we are at effective modulus of 0.6. And this is 0.6 relative to the highest value that the effective modulus can have. And the highest value corresponds, basically this is relative to the case where overlap of strength approaches infinity. Okay, so at infinity, we will have a modulus that you can easily calculate it. Basically, when lambda L goes to infinity, this value, when lambda L goes to infinity, this value approaches 1. Basically, the denominator will be dominated by lambda L, which lambda L goes away with this. So E infinity will be 2 elastic modulus of the brick times B divided by 2B plus H. So effective elastic modulus will be primarily at 100% at very long overlap length, will approach to that of the brick, because you can imagine if H is much smaller than B, then this can approximately be equal to the same as the elastic modulus of the mortar. So I'm going to stop this video, and we are going to continue on the next video.